Alors on a fait fort parce que le deuxième exposé va aussi être en anglais par Peter Solidaire de chez STORZ. On rentre dans un organisme de formation continue où l'académie se propose aussi de former en anglais, peut-être, non? Alors, Peter Solidaire de chez STORZ qui va nous parler des conditions d'utilisation de la fluorescence pratique.
Mr. President, thank you very much. I'm sorry that I have to speak English. My French is so poor that it would not be a pleasure for you if I would try to do it. But it's an honor and a pleasure to be here. And I would like to do a step backwards than Sylvain has presented. He gave, I think, a very good motivation what is possible. And our duty as a company, our try is to make physics and chemistry working, that the surgeon could be supported in his daily practice. And this is what I would like to present now to you. Fluorescence, simply speaking, and my fellow physicists would not like this, what I say, it is just using light to generate light, because we have either endogenous molecules in the body which are interacting with light, or we can introduce, as Sylvain has already mentioned, we can introduce drugs, contrast media, which are reactive. And what is the benefit for you? In laparoscopic surgery, you have lost one sense, this is palpation. You need to look and maybe testing, but not the direct way with palpation, what is happening and what are you seeing? You use your eyes, and even with the most sophisticated imaging technologies in white light, maybe you are missing. Your experience is helping you, but you have colleagues who maybe need some help. And if we think about functional imaging, if we need to know something which is happening, whether an anastomosis is working, whether the anatomy of the biliary tree is intact as you expected, you need maybe some additional information, and fluorescence could help, because fluorescence is a technology which allows you to see. We can use different colors to make these changes, to make this function visible. Just give me a few words for the company. Karl STORZ is a family company founded for over 70 years by Dr. Karl STORZ, and it's now headed by Mrs. STORZ, and her son is already a member of the board. And the product range we have is from instruments over imaging up to the integrated OR, which allows communication not only within the OR for the different instruments, but also between ORs. But now, coming back to my talk, I will talk a little bit about fluorescence, fluorescent dyes, medical devices, and last but not least, near-infrared imaging, which is currently, I think, one of the main topics on fluorescence imaging. And what we need in fluorescence imaging is a good combination between the dyes and the devices. The devices have to be tuned in such a way that we are able to make the fluorescent dyes visible. This technique is interesting, but it takes time to get the translation from development into clinical routine. And scientists are working, I think, nearly now 20 years on fluorescence imaging, and still it is not in routine. Well, what we experience is, and know that also for other technologies which are commonly used today, it takes time. There is a certain time needed from first patient until it is part of the clinical routine. Depends on how easy to use, depends on the cost, depends on reimbursement. and of course, last but not least, on the usefulness and the benefit for the patient. But it takes time. And I like these meetings because it allows to see where, for us to learn, where are the hurdles from your experience for these technologies. Fluorescence. Fluorescence, the name comes from the mineral fluoride, and it shows a certain aspect if we are using normal white light. But if we are going to use UV light, it shows a completely different color, and that is related to a physical phenomenon which is described here. A photon which has a certain energy is taken up, is absorbed by an electron, and this electron goes into an excited state by taking the energy from the photon. This excited state is not stable. It is very short-lived, and normally the photon goes back, the electron goes back into the ground state again, but sometimes it goes into an intermediate state by non-radiant relaxation. But it is losing some energy. And then from this intermediate state, it goes back into the ground state by sending out another photon, and which has a less energy. And this is depicted by the different colors. Short wave, like blue light, has a high energy, whereas long wave light, like red, has a shorter or lower energy. And this is what we use. It sounds simple, and as long as we are in an environment where we can use big machines, it is easy. But we would like to use it in minimal invasive surgery. Professor Zhu showed some examples for open surgery, but today, where minimal invasive surgery is becoming more and more used, we need to put it into small equipment which allows the detection of fluorescence imaging. We need two parts. One part is the fluorescence dye, or sometimes it's also called fluorescence marker, or fluorophores, or fluorescence dye, but it is describing or meaning the same. A substance which is able to take up the energy of light, of a photon, and send it out in a different color after a certain time. The chemical properties are described here. We need double bonds, like we know from benzene rings, and there has to be so-called delocalized p electrons, and the p electrons are very prone and keen to absorb photons and then do the procedure as I have described to you. There are a number of materials which have this property. These are either endogenous, tissue intrinsic fluorophores, or exogenous fluorophores. And on the next slide, I will show you the endogenous fluorophores that are structural proteins, porphyrines, lipids, vitamins, amino acids. So we can also use equipment for delineating certain areas inside the body without providing exogenous fluorophores. Exogenous fluorophores are cyanide dyes, photosensitizers, and so-called molecular markers like the green fluorescence protein. Currently, only, I would say, 3 of this long list of fluorescence markers are available commercially and approved by the authorities. This is 5-ALA, 5-aminolevulinic acid, which is primarily used in brain cancer surgery for the delineation of glioblastoma. 5-ALA esters, which are approved for the imaging of bladder cancer. And I think the currently working horse in this list is indocyanine green, ICG, which is used for perfusion imaging, imaging in, for lymph nodes, or in cholecystectomy. And there are many others in under development, specifically labeled tumor markers, but unfortunately it takes some time to get clinical approval. And I was working in the pharmaceutical industry, and I'm an optimistic person. I think maybe in 3 to 5 years we will have this fluorescence marker, this new fluorescence marker available. If we look at the imaging chain, we have a light source, we have a light cable to combine it with the telescope and camera system, we have a monitor, and we have archiving system. And primarily the first three are effective and have to be adopted and optimized for fluorescence imaging. There are certain techniques for the light source. One is xenon-based, and the other technique is LED or laser-based. Xenon-based has certain property or certain advantages if we think about different fluorescence markers, because we can use filters and adopt the system to the specific fingerprint for the fluorescence marker. On the other hand, LED and laser have advantages regarding the lifetime of the light bulb, but and also the energy provided to the fluorophores. And what is the best, I don't know, but I think as we see in the consumer market, it will go to this area of LED and laser, because you can work specifically and with this type of light source. The different companies which are using this type of light sources, Karl STORZ, obviously, Olympus, Photonic Eye, that's a system for open surgery from Hamamatsu. And then we have companies like Novadax, Stryker, Quest Medical, which are providing a system for laparoscopy. Of course, robotics, the Da Vinci's robot also has a fluorescence system. Then the open surgery system, Fluobeam from Fluoptics, this company from Grenoble, which is providing a very interesting and nice system, and Vision Sense with Stereo. What is happening? If you have a light source, the light source is, the white light is containing all colors of the rainbow, and for fluorescence imaging what you need is a selection of the specific light which is necessary to do the excitation of the fluorophore. So what we do in our system is provide or place a filter into the light path to select the specific wavelengths. And since this signal is pretty high and pretty strong, we need to detect the fluorescence response, the fluorescence signal, another light filter which is placed into the endoscope to decrease or block the excitation light. And then we see the fluorescent signal and can discriminate the fluorescent signal from the background, or in this case we are working with near-infrared, can discriminate it from the illumination of the background. The challenges we are facing are either related to software. We need the signal amplification if the signal is pretty low. We need the right density display, that's the quantitative information Professor Zhou were addressing. And for example, in bladder cancer, so-called PDB, the signal is so weak that to have it displayed here, there is an amplification necessary. This is normally done by summarizing images, frames, and adding it to it. And so the weak signal could be shown and displayed. Quantification, I think that's could either be done in the way that the signal intensity is measured, or the increase of signal intensity is measured and displayed, and could be an indication of the viability of an anastomosis. The hardware challenges I already mentioned is we need to have the right specific light for the excitation. We are currently working either with laser, LED, or with standard light sources where we use filters. The trend goes to laser diodes or LEDs. We need broadband filters, on the other hand, are cheap, but have also their limitation. Light cables, of course, need to have a high fluorescence transmission, should be autoclavable. Endoscopes have smaller dimensions, and therefore means, of course, that there is less light coming to the camera system, so we need this amplification. Currently, fluorescence is limited to rigid scopes, so for laparoscopy, that's not a topic, but if you think about looking from the mucosal side in the bowel or rectum, you need a flexible scope. And work on this is ongoing, but such scopes are not available. I would like to stop here because I'm already over my time, because near-infrared fluorescence was partly introduced by Professor Joe, and I think all the esteemed speakers following me will address near-infrared fluorescence. Near-infrared fluorescence has one big advantage. First, it is invisible light use. That means it's not interfering with the white light. And the big advantage is that this near-infrared light has a higher penetration into tissue. Normal fluorescence and normal white light is only showing you the surface of the organs, but with near-infrared you can look up to 1 centimeter below the surface into tissue. Thank you very much.
Thanks a lot. This is open to discussion. Yeah,
Thanks a lot for your communication. I want to ask if you think that in the near future it will be possible to perform 3D laparoscopy and fluorescence.
Yes, it will be possible. It's not such a big issue, because you can use the same technique you are using in 2D by either filter for the light source, that's not changing, or another filter system inside the 3D system. So you are blocking also the excitation light, and that's feasible. That's not, I wouldn't say that's rocket science.
But it is in the tube. It will be available in your company in the next future.
That's a difficult question. Let's put it this way. I wouldn't exclude it that this is a viable option for us. It's either 3D, or it's maybe like Intuitive is doing it. You have a 3D white light image, and maybe you have a fluorescence 2D image with a very good background solution. But
okay.
if 3D by itself is interesting, and you expect more information, that's important to know.
Okay.
As a urologist, I'm convinced with the interest of this technique for bladder cancer diagnosis, especially in situ. But you know, for decision making during at surgery, in terms of vascularizing or bad vascularizing of such anatomical part, I'm not so sure, and I'm not convinced of the interest of the technique. This is one point. And also, do you have also in your plans the projects for photodynamic therapy? Because this is another question, another development of this technique.
Coming to your first point, I think I'm maybe not the right person to answer it. That's what I would like to your surgical colleagues to answer it, whether this is viable. And even if this technique is available for 14 years or even more than 14 years, I think still the clinical investigations are under development. We are learning because a couple of years ago, primarily it was available for open surgery. And that had limited, in my opinion, limited areas of application. Whether it is useful for any indication or any potential questions, I don't know. I don't think so, honestly, from my side. But there are definitely clinical applications where it is contributing very much. To your second question regarding photodynamic therapy, there were some activities in the past also supported by our company. Here we have the same problem that we had in the past with the fluorescence dye. There has to be fluorescence dye suitable for not only diagnosis but also for therapy. Maybe it's different dyes, which has to be easy to handle. There are some markets on the market, but you have to inject them 24 hours or even more before doing the illumination, and then the patient has to be kept in the dark for maybe a couple of days, even a week. So that, I think, is not suitable. Here again, that must be the combination between pharmaceutical companies and medical device companies to make such thing working. And regarding bladder cancer, I think that could be a good idea to have your usual TURB, where you do the resection, supported by fluorescence, and then have an illumination for a certain time instead of using some chemotherapy. To answer your question, yes, that's interesting, because that's a step forward from diagnosis to therapy, but we have to have this right fluorophores. Then it could be done.
Yes, Peter, just last question. You say it clearly shows the limits of glioblastoma. Do you think it's accurate enough to avoid the pathological examination of the specimen?
No. We know from other indications that there are false positives, and for glioblastoma there are positive results. Life expectancy is prolonged, but as we know, it is not, the patients are not healed. So I think we have to do still biopsy. Personally, I believe that's a guidance in general.
Well, thank you very much.